Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to predict an election. The prerequisites for this material are continuous and discrete random variables. The goal is to illustrate some important concepts in probabilistic modeling through an idealized example based on the United States presidential election. So let's start by going over some details about how the United States presidential election actually works. It is an indirect election where citizens of the United States cast ballots for electors in the Electoral College, who are then the ones that select the president and the vice president. The number of electors from each state are equal to the members of Congress. So large states such as Texas or California or New York have many more electors than smaller states like Rhode Island or Delaware. Washington, D.C. gets 3 electors. So for the purpose of the US presidential election, there's actually 51 states. All electors in a state are typically assigned to the candidate who wins that state. So for example, if a candidate wins California, they will get all the electors from California, with 2 exceptions, Maine and Nebraska. Okay, so how do people go about predicting the result of an election? You might have heard, for example, about the 538 prediction model. Well, what they do is they use poll data to predict the probability that each candidate wins in each state. So let's define a random variable vi, which is equal to 1 if candidate A wins state I, and is equal to 0 otherwise. Once you have done that, once you have predicted the probability that each candidate wins in each state, you have to aggregate all of those probabilities to determine the probability that the candidate wins the whole election. We're going to represent that by the random variable e, which is equal to 1 if candidate A wins the whole election and to 0 otherwise. What do they need to do to win the whole election? They need to get more electors than the other candidate. This is represented as follows. We're going to multiply each vi, which is equal to 1 if candidate A wins and 0 otherwise, by the number of electors in the corresponding state, and then we're summing them over the 51 states. So this basically gives us the number of electors won by candidate A. If that number of electors is larger than half of the total electors, then that candidate wins the election. Okay? So this sounds pretty straightforward, but there's a catch. The catch is that you have to estimate the joint distribution of V1 to V51 in order to be able to estimate this probability, okay, because it depends on all of them. So it's not enough to just characterize the probability of each vi equal to 1 or 0. You have to worry about them being equal to 1 or 0 simultaneously for different states. Okay, that's what the joint distribution tells us. But you know, that doesn't seem that problematic. We have a mathematical object that deals with this. That's just the joint probability mass function of all of these random variables. So how about you just estimate it from data and don't make such a big deal out of it? Well, okay, so how many entries does this joint PMF have? Think about it for a moment. There's 51 states, so maybe I'll even write it down. So this is the joint PMF of V1, V2, up to V51. And each time, each entry, like for example, the entry 0, because candidate A does not win the first state, 1, they win the second state, up to maybe they win the last one. Okay, the entries look like that. How many possible entries are there? Well, we can put a 0 or a 1 in each of these slots, and there's 51 of those slots. So there's 2 to the 51 entries in the joint PMF. That's more than 10 to the 15. That's an insane number. You're never going to have enough data to compute all the possible entries, to compute all the possibilities. So what can you do, right? This is exactly the curse of dimensionality. We already discussed that. When you have several random variables, it turns out that unless the number of random variables is actually very, very small, you're typically never going to be able to compute all the dependencies between the random variables from the data, in the sense of being able to compute the full joint PMF. And if you have continuous random variables, it gets even worse, obviously. So what do you need to do? You have to assume independence or conditional independence. Okay, so in this case, assume that the outcomes in each state are independent. You say, like whatever happens in California does not affect whatever happens in New York. In that case, this joint PMF between V1, V2, up to V51, what happens to it when all of them are independent? Well, it factorizes, right? It's equal to the product between the product of the marginals. So now, how many numbers do we have to estimate if we assume everything is independent? We just need to estimate these individual marginals, and each marginal is just given by one number. Here, by the way, this -1 is because the joint PMF has to add up to 1. I forgot to say that. It obviously doesn't matter, like more than 10 to the 15 or more than 10 to the 15 minus 1 doesn't make a huge difference. Here, each of these guys depends on a single parameter, the probability that the candidate wins that particular state. And that's all we need, right? One parameter for each of these marginal PMFs. We just need to estimate 51 numbers, which sounds pretty doable, right? Okay, so why don't we just assume independence and call it a day and not make such a big fuss about it? What could go wrong? Well, this is the prediction of the Huffington Post for the 2016 election, and you might remember that this prediction turned out to be not entirely correct. So I'm not trying to make fun of the Huffington Post prediction. Like, everyone was wrong about the 2016 election. Why? Because the polls strongly indicated that Clinton would win, but then there was a systematic shift on election day, and it's not completely fully understood why the polls got everything so systematically wrong. But part of the problem was not introducing enough dependence and enough uncertainty. I said two things, right? On the one hand, enough uncertainty about what kind of voters were going to show up on election day, and on the other hand, enough dependence between what was going to happen in the different states, right? So if something started happening in one of the Midwest states, then it was, to be expected that it would also happen in all of the other Midwest states. But the models did not fully account for that. Again, I'm not trying to make fun of anyone here. Predicting a real election is extremely, extremely difficult. Here we're just going to take inspiration in this election in order to showcase some of the challenges of real probabilistic modeling, and how, in particular, independence assumptions can dramatically affect your final results, so you really need to be careful about them. But at the same time, you need them, right? Like, there's no escaping the fact that you need them. You're never going to be able to estimate the full joint PMF of the 51 states. That's just not going to happen. That's out of the question. Okay, so let's take a look at our cartoon United States election. We're going to simplify everything so that we can do, some math and illustrate the important points. Obviously, estimating a real election is super messy. There's a lot of details that you need to take into account. We're going to, bypass those details and just talk about this important point about how independence affects things. Okay, so we're going to have still 51 states, but now we are going to have one elector per state. Okay, so all the states are the same in our cartoon election. Whoever wins more states wins the election. The result in each state, we're still going to model with a random variable VI that is equal to 1. In this case, if the Republican candidate wins, just to make it more concrete, 0 otherwise. The result of the whole election is going to be E. It's going to be equal to 1 if, when you sum up all the states won by the Republican candidate, it's greater than 25. Okay? If that happens, then the Republican candidate wins the election. Okay, so now we're going to assume that we have used poll data, we have analyzed each state, and in each state, we actually reach the same conclusion. This is just to simplify calculations. Of course, this would never be the case. Alaska is not going to behave in the same way than, say, New York. But in this particular example, we find that in each state, the fraction of rural voters that are going to vote for the Republican candidate is 60%. And the fraction of urban voters that are going to vote for the Republican candidate is just 10%. Okay. What is the problem? The problem is that we don't know how many rural voters are going to show up on election day. That's uncertain. And by the way, this is a big thing predicting elections, at least where Trump has taken part. It's actually difficult, very difficult to predict what kind of voters are actually going to show up on election day, which is why predictions have been one of the reasons why predictions have been somewhat inaccurate. Okay, so how are we going to deal with this uncertainty about how many rural voters are going to show up? Well, we're going to model it with a uniform random variable Ri that tells us the fraction of rural voters out of the total number of voters in state I in election day. So if Ri is equal to 0.5, half of the voters on election day for state I are rural voters. We're going to assume in this first model that all of this rural turnout is going to be independent. Okay, so now, conditioned on the rural turnout, we know the probability that the Republican candidate wins state I because we know how many of those rural voters are going to vote for the Republican candidate and how many of the urban voters are going to vote for the Republican candidate. So out of the R rural voters, 0.6 are going to vote Republican. Out of the 1 minus R urban voters, 0.1 are going to vote Republican. So for that state, the probability that the Republican wins is just 0.6 times R plus 0.1 times 1 minus R. But of course, we're not interested in just conditioning on R, right? We want the probability that the Republican candidate actually wins that state. So here we have a conditional of a discrete random variable given a continuous random variable, and we know the distribution, the marginal distribution of the continuous random variable is just uniform between 0 and 1. How do we compute the marginal of the discrete random variable? We just integrate over the product of the marginal PDF times the conditional PDF. I just said that exactly the other way around, right? The marginal PDF times the conditional PMF of the discrete random variable given the continuous random variable. Sorry about that. I'm trying to pronounce rural in a semi-decent way. It just takes too much brain power from me. I don't know if you've watched 30 Rock with the rural juror. Anyways, so we set up this integral. It goes from 0 to 1 because the marginal of the rural turnout is equal to 1 over there and 0 otherwise. So, we plug in 1 for this, and then we plug in the conditional PMF, which is equal to this, and then we integrate from 0 to 1, and what we get is that the probability is equal to 0.35. So the Republican candidate has a 35% probability of winning each state. Again, to make things easy, we've just said that each state behaves the same. Obviously, this would not happen in real life. Now we have to aggregate all of this to figure out who wins the election. So under our assumptions, the probability that the Republican candidate wins each of the states is 0.35. Great. Also under our assumptions, we have assumed that the rural turnout in each of the states is independent, and because this only depends on that rural turnout, then those are also independent. Okay, so now we can ask, what is the distribution of this sum, which is equal to the number of states won by the Republican candidate? So that's just the number of VIs that are equal to 1 out of 51. They each have the same probability of being equal to 1. They're all independent. This should ring a bell, so think about it for a moment. This is just a binomial with parameters 51 and 0.35. Okay, so it's a binomial with those parameters. If we want the probability that the binomial is larger than 26, we just have to add the PMF of the binomial from 26 to 51. Okay, so that's the probability that the Republican candidate wins the election. You do that with a computer, of course, and you get 1.4%. Okay, 1.4% is the probability that the Republican candidate wins the election. it seems extremely, extremely, extremely unlikely, just like it seemed extremely unlikely that Trump would win the election in 2016. But is the independence assumption reasonable? Well, as I kind of explained a little bit before, not really, right? Like, I don't know, if people in like rural voters in Nevada start, go to vote, a lot of them go to vote, then probably in Arizona they're also going to go to vote. Right? I don't know if Arizona and Nevada are that demographically similar, but the Midwest is a very good example and actually had a huge influence in the 2016 election, right? So if in Michigan there's a sudden shift and rural voters come out to vote massively, then that probably is also going to happen in Wisconsin, and something like that. Of course, this is super idealized, but like this kind of effects happened in the 2016 election. Okay, or the other way around, right? Like the urban voters suddenly don't go out to vote because they read something in the newspaper or something like that. Okay, so in order to model that, let's take a look at an alternative model where we have a rural turnout that is shared across all states. So of course, in practice, you would not share it across all states. You would try to determine dependencies between states that are similar in some ways, okay? But we're going to go with this. We're still going to model it as uniform between 0 and 1. The important difference now is that there's no individual rural turnout for each of the states. They all share the same rural turnout. Okay, so apart from that, we're still going to consider that V1 to V51 are conditionally independent if we know the rural turnout. So if we know the rural turnout, they're still conditionally independent. They still, we still have the same fraction of rural voters voting Republican, the same fraction of urban voters voting Republican. Okay, so now conditioned on a certain fixed rural turnout, the Republican candidate is going to win state I with the same probability as before, right? 0.6, so is the probability that they win state I. It's going to be 0.6, which is the fraction of rural voters that vote Republican times the fraction of rural voters, plus the fraction of urban voters, which is 0.1, who vote Republican, times the fraction of urban voters, okay? So it's still the same. So now, what is the marginal distribution of them winning state V1, for example? What's the probability that they win state V1? What do we need to do to get that probability? Well, the same thing as before. We just need to integrate this with respect to the uniform. We're going to still get 0.35. So interestingly, under these two models, the probability that a candidate wins each individual state is exactly the same. Okay, just because the rural turnout has the same distribution, but there's a crucial difference. So what is the crucial difference? And I want you to think about it yourself here for a moment. The crucial difference for predicting the whole election, right? Because we want to predict the whole election. We don't want to predict states separately. The crucial difference is that the results in the states are actually completely dependent. Before they were independent because they would depend on each of the individual rural turnouts. Now we're conditioning on the same thing. We're conditioning on the same random variable. So we cannot just assume that they're all independent and say, oh, they're binomial. Okay? That's the crucial difference. Okay, so again, the rural turnout, I forgot to, I should have flipped this slide before. Realize that the marginal distribution, so the probability of them winning each individual state, is exactly the same, still exactly the same. Okay, the difference is going to be the outcome of the whole election. To see why, let's actually compute the probability of the outcome of the whole election, so the probability that the Republican candidate wins the whole election. For that, what do? We look at the conditional given the rural turnout, and we integrate against the marginal of the rural turnout. Okay, so no surprise there. What is this equal to? This is the probability that the Republican candidate wins the election. We have to sum over all the states that they win and see if they're larger than 25, but we're conditioning on the rural turnout. Okay, so if we condition on the rural turnout, we fix it to R. You can imagine that R is, 0.5, 0.6, whatever it is. With a fixed value of R, what is the distribution of this? Well, each VI is going to be equal to 1 with probability 0.6 times r plus 0.1 times 1 minus r. And this r is fixed for all of them. So they all have the same probability of being equal to 1. So we have 51 random variables, Bernoulli random variables, all with the same probability of being equal to 1, which are conditionally independent given this. What is that distribution going to look like? It's again a binomial, but the crucial difference is that now it's a binomial with this parameter conditioned on r. And so theta is that, and the n parameter is still 51. The crucial difference is that before, because they were all independent, we could just compute the individual probabilities by integrating against the marginal of the rule turnout before, and then just apply realize that that's a binomial. Now this is only a binomial if we condition on the rule turnout, okay, but not if we marginalize over the rule turnout. Then that doesn't happen anymore because you have all of these dependencies that you're not accounting for, because they're only conditionally independent given the rule turnout. Okay, that's the crucial, this is the important thing to understand here. But here we only care about the conditional, and then we will worry about integrating against the marginal, so we can actually plug in the binomial distribution there. The probability that this sum is larger than 25 is just the sum from 26 to 51 of a binomial with this parameter theta and 1 minus theta. Okay, that's where that comes from. And here we have substituted this by the uniform between 0 and 1. And that's why, by the way, this was between 0 and 1 from the beginning. Okay, so now we get this really ugly looking integral. I wouldn't be able to compute it. Out of curiosity, I kind of looked it up, and it turns out that you can actually compute it exactly by using some tabular values for Euler integrals that are related to the beta random variable that we're going to talk about in the next video. But this is just because we made a lot of simplifying assumptions. In more complicated probabilistic models, you're going to end up with an integral that you for sure cannot just solve by hand. So then what do? We already talked about this situation where you have a probability and you cannot really actually compute it exactly by hand. Let's see if you remember. This was a long time ago. Basically what we said is just simulate, use your model to simulate E many times, compute the empirical probability. And that's called the Monte Carlo method. And that's exactly how people do probabilistic modeling in practice, in particular, how they model elections. So they predict the election over and over and over again. So what if we don't know how to compute the integral? We simulate. And actually, we never know how to compute these integrals. We just simulate. So let's make it clear. What do we mean by just simulate here? According to an alternative model, right? So we're going to simulate 10 elections. The first thing we need to do is to generate a rural turnout for all of the states. We're going to call that RJ for simulation J. J refers to the simulation we're running. Okay, so RJ, for example, is going to be equal to 0.6. Then what do? We simulate the outcome in each of the states based on RJ. So we condition on, let's say, 0.6, I hope I said, or something like that. And we generate the result in each state. Okay, so Republican, state 1, Republican wins. State 2, Democrat wins. State 3, Republican wins, and so on and so forth. And then we see who won the election, right? We count who won more states, and we set EJ equals to 1 if the Republican won more states, EJ equals to 0 if the Democrat won more states. And then basically we just, after doing this for n elections, like 1,000,000, for example, we compute the fraction of times that the Republican won, and that gives us a good approximation to this integral. Okay, this is going to give us exactly the same result as this integral if we take, enough tries. And again, this is what is always done in practice. Okay, so I went ahead and did this. And remember that under our independent model, where rural turnout was independent, we got a 1.4% of probabilities for the Republican candidate to win. It turns out that under the alternative model, the probability is 20%, so 1 out of 5 times. And something that happens 1 out of 5 times happens pretty often. So, this is kind of close to what happened in the 2016 election. Here, I just wanted to show you, this is what the probability of each candidate winning a certain number of states looks like under the two models. So under the independent model, in blue we have the number of, in blue is the number of states such that the Democrat wins the election. So if the Republican only wins like 10 states, then the Democrat obviously wins the election. So the cutoff here is there at 25. So, if we end up in any of these blue points, then the Democrat wins. If we end up in the red ones, the Republican wins. And this is under the independent turnout. Under the independent turnout, what we see is that this is very peaked here because of the independence assumption. Okay, it's actually a binomial, as we saw. So it's a binomial. What happens? Basically, there's a relatively low probability that the Republican wins each state. Because they're all independent, it's unlikely that just by chance there's going to be a lot of them that flip. Okay, because they're independent from each other. So in most possibilities, like some of them flip, like some of them are Republican, some of them are Democrat, but more of them are going to go for the Democrat. Because they're all independent, it's unlikely that they will all go for the Republican at the same time. This changes for the dependent turnout, because if it just so happens that the turnout for rural voters seem to be high, turns out to be high, then for all the states, it's more likely that the Republican will win, and that's what captures the dependence. And because of that, we have a much fatter tail here, where the Republican can actually win if the rural turnout happens to be high, because in that case, the probability of all of the states together, the probability that the Republican wins in all of the states goes up together. And this kind of captures this idea that if voters start behaving in a certain way in a certain state, they're going to start behaving in the same way in similar states. And it's crucial to account for that if you want to adequately capture our uncertainty about the election. Okay, so what have we learned? We have learned some common ingredients for practical probabilistic modeling that is applied to estimate things such as presidential elections. This includes model design, so you have to know how the presidential election actually works to build a model adapted to it. So in this case, you have electors in each state, so you have to figure out what happens in each state, then you have to aggregate and so on. You're going to have to make independence assumptions, okay? I'll talk about that in a moment, but during the model design, I really want to say that a big part of it is at some point you're going to find a joint PMF. It's going to be intractable to estimate it, so you're going to have to assume conditional independence or independence. Then after you're done with your model design, you're going to actually solve your model to compute some probabilities. That is going to use Monte Carlo simulations, like for almost any practical situation. And then going back to the independence and the conditional independence assumptions, these are crucial and they're going to have an enormous effect on your conclusions, the conclusions coming out of your model. And this was a huge factor in the predictions for the 2016 election. Thank you very much.